All right, let's take a look at problem 1486. Here you're being asked to calculate the pH of a diprotic acid solution. And these are always fun ones because you get to work an ice chart first. You get to work an ice chart twice, essentially. Let's take a look. We're given the polyprotic acid, oxalic acid. And the first thing it's going to do is it's going to lose one proton. And form the amphoteric ion monohydrogen oxalate. Our initial concentration is 0.21 molar. Now, this number is randomized, right? So the number that you are looking at in your homework is probably different than mine, which means you get the joy of working this all on your own after you see how I do it. You have no protons to start off with. You have none of your conjugate ions. So your change is minus x, plus x, and x. Your equilibrium amount is 0.21 minus x, x, and x. Set up your Ka, your Ka1. Now, unfortunately, we want to make the assumption, right? There is nothing more we would like in this world to say that 100 times our Ka is much, much less than what we're subtracting it from. Unfortunately, if we multiplied 100 times 5.9 times 10 to the negative second, it would wind up being greater than that. So we are stuck doing the quadratic equation. So buckle in for a fun time of algebra. So first thing, I'm going to bring my bottom numbers up. So I'm going to multiply both sides by my 0.21 minus x. That, of course, crosses it out. Then I'm going to distribute this into my parentheses. So that gives me x squared equals 0.0123. My handwriting got really sloppy there. 0.01239 minus, that's a 9, minus 0.059x. Now I've got to bring it over to the other side. So that's x squared plus 0.059x minus 0.01239. A, B, C, And of course, we are doing the opposite of b, plus or minus b squared minus 4ac divided by 2a. So a 0.059 plus or minus the square root of 0.059 squared plus 4 times 0.01239. And yes, I know that I have a negative in the formula, but I've got a negative c, right? So a negative times a negative is a positive. And you really can't read that when I ran out of screen there. So let me go to, well, you're going to have to because now it won't let me erase. Divide by 2. So that, now I punch it into my calculator, 0.059 plus or minus. I take that quantity in there, and that gives me plus or minus 0.2, oh, come on, 2303 divided by 2, which gives me, well, first of all, do I use the plus or the minus? Well, notice that I've got a negative here in front of my b, and you can't have negative matter, so you have to go positive. Otherwise, you wind up with a negative number. So it's going to be negative 0.059 plus 0.2303, and that gives me x is equal to 0.08565 molar. So what does that mean? Good question. Let's go back to our ice chart. We go back to our ice chart. No, I'm through with you. I want the ice chart. There we go. And that means that our concentration for our first equilibrium of our hydrogen ion concentration is 0.08565, and the concentration of our weak acid is also going to be 0.08565. We need these concentrations in order to work our second ice chart. Now, if you listen to the pre-lab lecture, not the pre-lab lecture, wrong class. If you listen to my lecture on polyprotic acids, you know there's a good catch coming up here that will save us lots of time. So let's get that second ice chart rolling here. Just need a good place to put it. Let's see here. Maybe I'll use color to help out a little bit. Here we go. Our second ice chart is going to take that amphoteric monohydrogen oxalate ion, react it with water, yield our hydrogen ion again, our initial amounts are going to be governed by the answers from our previous ice chart. So our initial amount here is going to be our 0.08565, 0.08565, and then we have none of that to start off with. Well, our change is going to be minus x plus x plus x. And x. So now let's set up shoot, it's not dragging and separating the way I want. Let's set up our Ka. I hope you're watching this on a computer monitor instead of your cell phone. You're going to go blind if you're watching on your cell phone here. Well, I'm going to blow this up again. Notice they gave us the Ka2 right there. Right? Everybody see the Ka2? So when I pull 6.4 times 10 to the negative fifth out of thin air in the next step, you know where it's coming from. All right, so we're coming over. We're setting up our Ka2 equilibrium constant. Ka2 is equal to our hydrogen ion concentration times C2O4 negative times our ion concentration, and it's all equal to 6.4 times 10 to the negative fifth. So your Ka2 is equal to x times x times 0.21 minus x. Whoops, what did I do? I was looking at my wrong ice chart there. Forgive me. I did that on purpose to try to confuse you. Of course, 0.08565 plus x times x divided by 0.08565 minus x is all equal to 6.4 times 10 to the negative fifth. Well, 100 times 6.4 times 10 to the fifth is less than 0.08565, so we can make the assumption. Subtracting x won't significantly affect the value. Neither will the adding of the x. That sounds like Starfire. Neither will the adding of the x. All right. So that gives us 0.08565 times x over 0.08565 equals 6.4 times 10 to the negative fifth. Well, any number divided by itself is 1. So that gives us that Ka2 is equal to x, which is equal to 6.4 times 10 to the negative fifth, which is what we expected all along. Because if you listen to the lecture, you'll remember that the concentration of the final conjugate base of a polyprotic acid is equal to the Ka2. Something to keep in mind there. Where was I going? Oh, and therefore pH, we didn't really change our hydrogen ion concentration from what we had to begin with. So our pH is simply going to be the negative log of 0.08565. And that was the hydrogen ion concentration we saw for earlier, way back with that first ice chart. So negative log 0.08565. So that gives you a pH of 1.07. And those are your answers for it. Oh yeah, just in case you were down here, just to make it explicit, remember that's the concentration that we're equal to. Oh, I should have had 2 negative there. Somebody's going to send me an email. Yeah, there's a 2 negative there, yes? Okay. That's it. Beep.